All right, so welcome everyone. Today in the computer vision course, I'm very happy to have three engineers or a manager as well from Kronos here. Concretely, I have here Alex, Max, and Thomas, and they work on inspection R&D at Kronos, and they will tell you more about Kronos now and the challenge, and you can ask any questions that you may have on the challenge. And then we'll continue with the lecture after this. So the floor is yours, Alex.
Thank you. Hello, everybody. My name is Alexander Hewiker. I'm an engineer from Kronos. We all three work in the research and development department of Kronos. And today we are here to issue a challenge to you, an AI challenge. And I think, can I see the slides? Are you already sharing slides? Maybe, should I share or do you want to?
So I didn't know that I was supposed to share the slides, so I don't have them at hand
I
at the
can,
moment.
no problem.
Okay.
I can share them. I think that should. Oh, let's see. Okay.
Otherwise,
Yes.
I have them at hand now. So shall I just go ahead with
Sure,
screen
please.
sharing? Okay.
Yeah. Yeah.
So we have already uploaded the slides also to the course in iLearn. So there you go.
Thank you very much. Okay, so Krones is a company founded here in Bavaria in 1951, and this year it's the 75th anniversary of Krones. And by now, Krones employs more than 21,000 people worldwide, and we have a turnover of 5.6 billion euros. And we produce machinery for beverage and liquid food companies. Our headquarters is situated in Neutraubling, close to Regensburg. And we also produce inspection machinery. So inspection machinery is used in the beverage and liquid food industry whenever some processing step needs to be verified. And we want to introduce to you one of our machines, and this machine is an AI machine. It's called Linatronic AI, and it's an inspection machine for returnable glass bottles. We build machinery for PET and glass and can and PET bottles, but in this case, this machine is only for returnable glass bottles. So whenever an end customer returns bottles to the supermarket and the supermarket returns the bottle to the beverage company, those bottles, they will be washed in bottle washing machines, and then they will be inspected for defects or any contamination that might be left. And this Linatronic AI is an empty bottle inspection machine that decides if the returnable bottle is reusable or not reusable. And to introduce to you this machine, we would like to show you a short 3-minute video. Could you please click on the first link, on the first linked video? I think holding down Control and clicking on should do the trick.
Unfortunately, it's not clickable.
Okay.
Do you have the video at hand? Because I didn't know I would need to share this. So if you have the video, maybe you can switch the screen share then.
Yeah, let's see. Just have to find the screen. Okay, here, screen sharing. Let's see. Okay, include.
Great. You would just remove the zoom from your window. Perfect.
Making them much smarter and more efficient than their conventional peers. No doubt about it, with its highly sensitive inspection modules, the Lenatronic screens every single container and allows only flawless bottles to pass. Whether it's material damage, contaminants, or minute caustic residues, nothing can hide from the Lenatronic. The inspector detects even the tiniest water droplets still clinging to the container after washing. And this is precisely where the crucial difference lies. In the new Lenatronic AI machine generation, containers with water droplets still adhering are no longer rejected in the base inspection unit, but allowed to pass, because the machine has learned a number of new tricks through deep learning. That is a technology enabling machines to do what we humans do naturally: learn from example. The foundation for deep learning is an artificial neural network that has been integrated in the machine's software. This can be described as a complex system of multiple filters. The Lenatronic AI uses these filters to classify the container images captured during the inspection process. The first filter's output becomes the input for the second filter, and so on. In this way, the complexity of an image's characteristics can be increased almost infinitely. The chain ranges from simply distinguishing between dark and light pixels all the way to detecting simple shapes or very specific objects such as water droplets. The neural network was therefore continually fine-tuned, using thousands of example images until it was able to detect not only the smallest of contaminants, but also other defects that used to be difficult to find, like glass splinters, for example. The system can dependably distinguish even water droplets from other anomalies with a reliability rate of over 99.9%. As a result, waste due to false rejects is no longer an issue. The time-consuming process of configuring the inspector during commissioning is also a thing of the past. This is because the neural network doesn't require manual calibration to local conditions. It is delivered fully trained, and the Lenatronic AI is immediately ready to start work.
I'll stop the sharing. Could you please reshare the slides, please?
They are coming.
Thank you. So the Lenatronic AI is a machine that has around 10 different cameras built in that inspect different parts of the bottle. And today we are only talking about one of those cameras. And this camera is the camera that inspects the base of the bottle. It's using a backlight to highlight any dirt in the bottle base or any defects. And we already saw some images in the video that showed the bottle base. On the next slide, we can see an example. Yeah, an example of two bottle bases, and one of them you should already recognize from the video. This is on the left side. This is a water droplet clinging to the lower, to the bottom or the base of the bottle. It's hanging on the outside of the bottle, and it's no problem for the product or for the end customer. On the right side, in contrast, we see a bottle that should be rejected because it contains a crown cap that has been crumpled and stuffed into the bottle. And in the past, we used, let's say, classical image processing technology to detect those dark pixel lumps in the base. But as you can see on the left side, there are some dark pixels produced by the water droplet, which are not really a defect or a contamination, and that bottle should not be rejected. So the goal and the challenge is to develop a vision model using any method that you know. Can be a CNN, or for classification could be a segmentation or anomaly detection model, but it should in the end produce, your code should produce a binary decision about, is the bottle reusable or is it not reusable? And of course, in the best case, it should outperform, strengthen, or meaningfully complement our solution. And why we use AI? As you have seen in the pictures, sometimes it's very difficult with classical image processing to distinguish those features. But with AI, we can train from examples, and we can make much better classificators for those decisions. As part of the challenge, we will provide you with a huge data set of about 50,000 images of bottle bases, and we challenge you to train the best vision model that you can come up with. On the next slide, there's another example of a bottle base, and this bottle base does not show any defects. It might look like that, but all of the visible features are not defects. So on the top left, we see this white streak, which is this is white glass that during the recycling process of the bottle has been introduced, and it's just a little bit brighter and no problem for the product or the end customer. The little dark dots, those are air bubbles in the glass. Those are created during production of the bottle, and they are no problem for the product or the end customer, so they can also be safely ignored. And the last example on the right side are some water droplets, and those can also be ignored. They are no problem to the product or the customer. And everything else that you can find in those pictures, all the kinds of the contaminations, should be rejected. So the training data, those 50,000 images I talked about, they are annotated, and they have polygons for annotations and labels with classes assigned to them. And yeah, your task is to train the best vision AI model you can come up with to distinguish the good and the bad bottles, and the reusable or not reusable. There's also, as an incentive, some prize money involved. I think on the next slide, there will be, the first 3 places will be awarded a prize money. Third place is 500 euros. Second place would be 1,000 euros, and the first place is 1,500 euros. And the way we determine the ranking and the winner is, first of all, for us, the model performance is very important for us. Model performance directly influences resource usage and economics of the machine. So the machine produces or inspects more than 70,000 bottles per hour. And if we can improve our classification just by a tiny bit, that results into many saved bottles that are recycled or reused instead of being crushed and then made into new bottles. We would like to maximize the amount of reusable bottles, but of course we need a certain quality and cannot have contaminations or defects in the good bottles and in the ones that are used for production. Second criteria is the model efficiency. This is also important. Of course, the building our machines costs money, and the hardware should be sized right, but not oversized. So if that can be solved with small hardware, then that would be better for us, because the production cost of our machines would be lower. So please keep in mind the model efficiency, and this will also be tested as described. And the third thing is more of a soft criteria. This is the most valuable insight. If you can come up with a valuable insight that helps us improve from our data set, then we would value that very much, and the jury, which will consist of experts, will judge if your insights that you present at the final presentation are worth a prize. On the last slide, there's a timetable or timeline for the challenge. The challenge is not yet live. It will be set to live shortly before the kickoff, which is 23rd of April. And I think you are asked to build teams and register in your iLearn application until 16th of April. And the final presentation of your team results will be on 27th of June. And also the first 3 places will be announced in June at the final presentation.
Yeah, thank you very much. I'll say a few words about the organization before we continue with the questions from the students. So first of all, I'm very happy about this opportunity working here with Kronos. Possibly quite some of the students know I worked at Kronos in the past until a long time ago, but when I was there, I established this AI competence center in the R&D branch of Kronos. And we also collaborated with you guys, Alex, because you were just working on that system at that time. As I remember, you were looking into deep learning, and we provided some input as well through my team. And then finally, after I left, it also appeared in the inspection machine and left the R&D phase and is now part of a product. So that's really cool. And what I like is we get real data, not just made up data, and data that the students would possibly not be able to find publicly. And I think that's really cool. Plus, you have multiple criteria you need to satisfy, not just the best performance, but also efficiency. Plus, ideally, you would provide us with some new insights as well. And there is some prize money. So I want to thank you for the commitment and all of this. Before I'll say more about the organization, maybe we'll start with the students. If there are any questions, and if there are, maybe just raise your hand here in Zoom, and then maybe turn on your mic and ask us the questions that you may have. So we have almost 150 students here, so I'm sure there are some questions. Or also in the chat. The question is in which language you would present. Since this course is taught in English, ideally all the presentations would be in English too. However, if you really want to present in German, then you can present in German. So, but ideally in English, but the mark will not depend on the language. And there was one question here, what the F1 score is. That's something that should have been taught in your machine learning course. So the F1 score is just a metric. I can mention it later also briefly in the class. But I know many of you are taking the machine learning course in parallel to this course, so you may have not seen it. It's just a metric to assess a model on a data set, and consists eventually of the precision and the recall. But I can mention this later in the lecture part. And there's a question here about the actual F1 score. Now I understand. Can you reveal? I don't know, Alex, you can tell us maybe if we will see in the challenge how good your system is, and then they know whether they bet it or not.
You do not have to beat our system to win a prize. You are only competing with each other. There's no such thing as the F1 score, because that depends on the test data, of course, on the different machines, on our different customers. Each customer has slightly different material, bottle material, and the F1 score varies for each customer. In our validation, of course, our F1 score is in the very high 90s. And we expect with the current training data, you should be it should be easily possible to have an F1 score around 95 or higher.
Okay, there's another question here in the chat. What you are actually providing to the students, which data? So I guess you provide the 50,000 images plus the label, right?
Yes, that's right. The complete training data, 50,000 images, fully labeled, including polygons for the folds and text labels on the polygons.
Okay, so some additional information. And then for the ranking in the Kaggle board, they need to upload, I think maybe you can tell a bit more what they need to upload in Kaggle. Is it predictions or their model? And do you have some validation set on which this would be run then?
You can use notebooks in Kaggle to load the data and also to process the data. The notebooks run in the same hardware environment at Kaggle, and every Kaggle account has, I think, 30 hours of GPU time per week or something like that. You are free to use that, and we will use the notebooks to also determine model efficiency and resource usage. The result that you are asked to upload is something like a text file with the sample name and then your binary classification, if you classified this as good or bad. And
Okay.
yeah.
And there's a question if there's a contact person from Kronos during the challenge. So whatever questions you have during the next few months, Alex will be happy to help you, I guess.
Yes, we would like to use the Kaggle forum. So if there are questions, everybody is able to see the questions and the answers, because otherwise people who are more inquisitive and ask more questions have an advantage. So please use the Kaggle forums to contact us after the challenge has been started and set to live, and then everybody can participate in the discussion.
And there's a question about a Kaggle account. So you would need to create a Kaggle account yourself, ideally with your university email address, and the access link will be provided at the kickoff. So for the, I'll say a few words about the organization and also quickly change my screen share so everyone is on the same page. So in our iLearn course, if you scroll down, you find this Kronos Challenge sign up. It will open in a couple of minutes. And there we got 40 groups and 2 to 3 students can be in a group. You would just join the group. And then you need to finish the sign up as soon as possible. At some point, the 40 groups will be filled, and it's limited to 40 groups because we need to do all of these presentations on one day when the guys from Kronos are free, and that's one Saturday. And we are really not able to do more than 40 presentations plus the ranking and all of this on one day. It's anyway going to be a very busy day for us. So it's 40 groups, and you ideally sign up as soon as possible at the latest April the 16th. And my wish would be that we really fill all the 40 groups because we have more than 200 students. So it's like 80 to 120 students can do this challenge and do the other regular projects. So you can sign up very, very soon then in this portal. And then for the organization, I would inform you about who finally gets signed up and all of this next week after the deadline. What's also important because I see your name in here when you sign up, but I also need to know your student ID later to register your mark in Primus, so you can edit the description of the group, and there you also have to write in the names plus the corresponding student IDs of your members. Otherwise, I don't know who signed up, or I see your name, but I'm unable to put the marks into our system at the end of the term. So please update the group description early. I've mentioned this here as well. And then in 2 weeks' time, we will have the kickoff, which is on campus for the students who are doing the Kronos Challenge. So in 2 weeks' time, we will not have a lecture, but we will meet at 2 p.m. on campus. I have put the room and all of this also in the iLearn course Concretely, it's a bit off campus. It's in Veilchengasse, which is just in the city center. And there we will meet at 2 p.m. And you have to be there. It's mandatory. And all of these presentations at the end of the term will be on June the 27th. So, meanwhile, there are many, many more questions that I guess we're happy to answer. Maybe you can tell us what are the most common defects among the bottles?
So there are generally two things we do not want. One is contaminations. That's everything that can end up in the bottle. So that can be crown caps in the summer, that can be popsicles in the winter, that can be fireworks, that can be chewing gums, all kinds of things end up in bottles. Most of that is washed out. Most bottles are clean, but a small percentage are not. About 1.5%, 2% of the bottles are rejected after the washing. And yeah, those defects, yeah, the most frequent defects, I would say, or contaminations are crown caps, and some kind of residue left in the bottles.
Yeah,
And the other question was...
Well, there are many more, so I summarized them a bit. One question is whether you can use your own model or a pre-trained model or an LLM. Well, that's up to the students. You can pick any model, any approach you wish for this. And that's why we have this challenge approach. So we rank you, we see how you can compete with each other. I think this will be a lot of fun. And so you can create your own architecture, use a pre-trained one, whatever. And we have hardware available through Kaggle. And there's a question whether it is actually manageable by students. Yes, well, the computer vision course is an introduction to computer vision, and you have to do a project anyway, which is the sole examination. And the course is meant that you're able to do this. And we've discussed neural nets last week. We finished them this week. This week, we will look at a few pre-trained architectures. You could use one of them, for example, and fine-tune it. A few students have asked also, there's a question whether you're allowed to use LLMs for coding. Yes, absolutely. You can use AI assistants for your coding because this is a real-world course. But you still need a model and all of this, and we will quiz you also on what you have done after the presentation. But any AI help you can use as long as you still know what you're doing. Is there a question? Because someone spoke. Well, I've muted that person since I didn't hear anything. There are some more technical questions about Kaggle. I guess all of this will be discussed then at the kickoff in 2 weeks when you see the actual platform. And there's a question, what's the speed of the bottling line? So typically, I guess, so
Yeah.
my understanding is like 50,000 bottles per hour or something, right? Or even
Yes.
more.
So 72,000 bottles per hour is a typical high-speed line, and that results into 20 inspections per second. So your model should be fairly swift. We do not only have one camera. As I said, the machine consists of multiple cameras. Multiple of those use AI. So when we process those bottles, we have about in the machine overall we have about 160 inferences per second, and that's about 1 gigabyte of data per second that's processed. For your challenge, it's easier. You only have to process data or images of one camera, and that's the base inspection camera. But keep an eye on how fast your model is.
Yeah,
That's important.
some more questions, including some private ones, because students from many different degree programs take this course. So in your groups, you can mix from different degree programs. If you have students from AI or cybersecurity, you can mix, as long as it's groups which are 2 to 3 students. There are also some questions about the marking, so I will also briefly address this. So don't be worried too much about a bad mark. If you're not at the top of the challenge. So you can score up to 50 points for your mark. And your presentation for the Kronos challenge will take 10 minutes. And because we have 40 groups one day, so what you should do is you would present us briefly with an exploratory data analysis. So maybe you have noticed anything in the data, any kind of anomalies or distributions, whatever. Then you would present your model, your approach, what you have done, and that would be 15 points out of 50. So for your model, this would quite have some impact on what you have done, and your performance in this challenge is up to 10 points. And what this means is progress and competition results. And if you commit to this, so we can later see whether you have done lots of attempts or if you only have submitted once a model for 2 hours and you are done, this would be reflected in this point here. But if you're not number 1, 2, 3, you can still get a lot of points here simply if you have committed to the project, because the top score will have impact on the prize money. But even if you worked very hard and you're not in the top 3, you can still get a lot of points here. And you would also present your lessons learned, maybe something that has worked and that has not worked. Plus, there will be up to 5 minutes Q&A in which we will ask some questions. So even if you're not in the top 3, you can still get a very, very good mark. And a lot of students actually get a lot of very good marks in this course. If you do a regular project, so not the Kronos challenge, you can also get up to 50 points, but everyone works on a different project. So the presentation would take like 15 minutes. And the marking scheme is different. There's also a Q&A session for which you get some points, some lessons learned. And for the regular projects, you would also present us with your motivation, why you have done this project. You would also present us with your methodology. Plus, for the regular projects, a demo is very important, that you show us something live, either how a system classifies or a robot or some other processing systems. So we not just see methodology, but something that runs. That's not too important for this Kronos challenge because you all have the same project and we simply want to see how you're competing and which model you have picked. So the presentation is a bit shorter and the marking scheme is different, but both marking schemes, if you work hard, can lead to very good marks. So don't pick or avoid the Kronos challenge just because of concerns around marking. What we want to see is that you've progressed and you've committed to this, and then you can still get a very good mark, even if you're not among the top 3, because we also have no clue how close those groups will be eventually, and how you spread out is something we are also surprised, or we are very curious to see. So that's about the marking, but you can only pick one of the options, either the Kronos challenge or a regular project. You cannot pick both or anything like that. And there's a question here: how accurate is the AI for contamination detection? And I guess you answered this before already, Alex. It depends a lot on the
Mhm.
actual bottles, on the customer, right?
Yes.
And for all the questions about Kaggle and the hardware available through Kaggle, these are all details we will see at the kickoff in 2 weeks. Some students, they have put they have written here in the slides. Maybe you can just remove this because it's being recorded. So we have this tick as well as something here. So it would be good if you just remove it. Are there more questions? The Kaggle Challenge, the ranking is live, right? So the ranking is updated all the time when there are new submissions.
There is a live leaderboard, yes. I think the F1, it's ordered by F1 score. The efficiency part will be determined by us after we finish the competition. I think that does not work live with the Kaggle tools. We have to do that manually.
Yeah. In the leaderboard, you'll have the model performance and also the most valuable insight. We will determine this during your presentation, so this will only be determined at the very end. But focus in the challenge, obviously, on your model performance and make sure that you're also at least somewhat efficient and maybe don't pick an overly complex model that delivers a slightly better F1 but is 1,000 times slower. Something like this should be maybe avoided. Are there still any questions we have not answered so far? I guess we have addressed all of those. In the meantime, you can also sign up for the challenge. This has opened, so quite some groups have already filled. If you haven't picked your group yet, you should do this quickly because they may fill actually
Yeah.
quite quickly. And it's constrained to 40 groups simply because we need to do this on one Saturday, and more than 40 groups isn't really possible. All right. If there are no more questions, there's one more now. Which programming language? You can pick any language as you wish. Typically, Python is the language we would choose, and this would probably work the best with the notebooks you have mentioned that run in Kaggle, right?
Yes.
Yeah. So I'm very excited about this and also see how the competition will go. And I think it's a huge opportunity that we get to work with this real data. And I think other universities like Stanford or TUM are jealous and they wish to see something like this too. Because getting such data, real data from classic engineering, is something we is an opportunity we don't have that often at universities. So I'm just very happy to do this with Alex and your colleagues from Kronos. Then thank you very much for joining. The
Yeah. Thank you very
so
much for
far
your
Alex
attention.
spoke. There is also Thomas and Max. Alex, I would just put your email in the iLearn course as a contact. Would that be fine, or shall I put all three email addresses as contacts?
Yes, that's fine. You can put my email. Be aware that any questions regarding the competition should be answered in the Kaggle forum, so everybody sees the answers, so it's fair. So if you have any inquiries regarding the content of the competition, please use the forums for that.
Yes, and for those who sign up for the Kronos Challenge in 2 weeks' time, we will then have the kickoff, so there will be no lecture in 2 weeks' time. And we meet on campus and see how to sign up for the Kaggle Challenge and all of this and any technical questions there may be. There's a question if you need to keep Kronos hardware in mind that is finally used. I
No.
don't think so. We just use the infrastructure through Kaggle. And there's a question about macro or micro F1. I guess we'll get back to that if necessary, but actually just F1, but I'll show you what F1 is now in a moment in case you have not seen it. Good. I guess Alex, Thomas, Max, thanks for joining, and I'll see you on campus in 2 weeks' time then.
Yes, thank you so much for the opportunity and have a nice day. Bye.
Take care. Bye-bye. So I'm also turning off my camera for the remaining lecture part. So for the F1 score, it's just a metric that allows us to determine how good a model is. And eventually F1 is the harmonic mean of precision and recall. If you're not familiar with F1, feel free to read, for example, this article here in Wikipedia, or it's something you would see in your machine learning course or something you have seen before. Because there are lots of different metrics like accuracy, whatever, but here for business reasons, Kronos have picked F1, which has a different objective than accuracy, for example. Yeah, so a lot of you have signed up already for this challenge, so I think that's really cool. And we'll continue now with the lecture part, and I'll say a few more words about the project. So I've mentioned these marking schemes, both for the Cronus Challenge as well as the regular projects. And with regards to the schedule, um, I have informed you via round mail that now this Cronus Challenge, this you can sign up until next week. Ideally, if you want to do it, sign up now because the places should be gone quickly. And for a regular project, you would need to sign up. Um, I can also share this quickly. For a regular project, you can also sign up in iLearn between April 17th in the morning and Thursday, the 23rd of April. And then the session on Thursday, April 30th. So in 3 weeks from now, you would do a quick proposal presentation presenting briefly what you want to do. I will share some more information via round mail in iLearn in the coming weeks. But these proposal presentations in 3 weeks, so on the 30th, it would be just 1 or 2 minutes per group with 1 or 2 slides, just briefly presenting what you want to do. But first, you need to submit just your topic and your student IDs and names and all of this via the submission in iLearn. So I can make a list and then we'll go through the list and you will give your proposal presentation on April the 30th. And so we'll have a lecture for the remainder of today, as well as next week, there will be a lecture. And then in 2 weeks, we have the Kronos kickoff for those who are doing the Kronos challenge. And for all the other students doing a regular project, we'll have these quick proposal presentations in 3 weeks. By the way, is anyone interested in doing a robot vision project? So for the ones doing a regular project, if you want to do a robot vision project, maybe just send a thumbs up or something, because so I see if anyone is interested for the regular projects. So I got at least one thumbs up now. Don't forget that you can pick your robot. No, if multiple thumbs up. You can pick your robot tomorrow morning. I had sent this reminder, and when we come to the agenda of this course, there is this Foundations of Mobile Robotics chapter. This one I'm not teaching this year because the schedule doesn't allow it to teach it this time before the proposal presentations, but we have the recording from last year in YouTube, so I have referred you to this, and all the recordings are available from last year, so you can watch this anytime in case you wish. Are there any other questions about organization of the course and so forth? If there are, please let me know. So there's a question now, if all the places for the Kronos Challenge are gone. Almost. There are 2 groups so far that have only one student. Those groups would still need to find at least a second person. There are some groups that have 2 members. They may be open to a third person, but ideally you would check this with each other and not just randomly join groups. And there's now one group left, group 25, which only has one student. He or she, I think he needs to find a second person. And those groups that have 2 students so far, they can still find a third person. So this is something you need to arrange. And then some groups have already started putting in the names matched with the student IDs. Some of the groups have not done this yet. So if you haven't done this yet, just update the group description. But the places seem to be gone quite quickly, which is something I'm very happy about, because then we'll have maximum turnout and a lot of competition in the challenge, and you get to work on a real problem, and maybe that can be a good opportunity for finding a thesis or internship or a job, whatever. And so that's something I am happy about now. Good. there's a question about the robot, which robot you can get. We have this platform here. We have other platforms too. This is some hardware I bought when I started my professorship 6 years ago. This is this Jetson Nano developer kit. The robots are already assembled. So the students that took the course in the first year when I taught this course, so 6 years ago, they had the opportunity to assemble these robots. Now they are assembled, and there are less left than we had in the beginning because quite a sum of the robots broke down, and we had to dismantle some of them to get spare parts. So we still got robots, but less than we had in the past. And for this robot, there's a camera here in the front. We have a GPU running on the edge, so you can run your computations on the edge if you wish. We are hoping to get new robots sometime in the future as funding would allow us, because this platform is now not really the latest platform anymore, but it still works well and you can run models on it. But go to the deep learning lab where this hardware is available, because Mr. Runkel, who is the lab technician for the deep learning lab, he also buys other hardware. So if you see any other hardware there that at least has a camera, some other mobile robot, some other robot, ask him if you can get it. As long as there is a camera and you can link it to a computer vision course, I'll be happy about it. So that's why I just visit the deep learning lab tomorrow. I'm there only infrequently. That's why Mr. Runkel is the right person to get in touch with. And for all questions on the robots or technical issues with the robots, always get in touch with Mr. Runkel, since he is there full time as a lab assistant for the deep learning lab and can probably help you the best. Or also, if your robot breaks and you need to replace a drive or whatever, he is the person to get in touch with. And he is doing terrific work. And for these theoretical foundations, you can just watch the recordings from last year, because this year the schedule is a bit different because of the Cronus challenge. Now, I guess I have answered all your questions, so we can go ahead with the lecture part. And last week we started with object recognition. We saw different object recognition tasks. We saw various challenges and approaches that allow us to do object recognition, such as template matching. Then we saw histograms, simple approaches that run very efficiently, but they can't deal a lot with noise or variations of the objects too much. And that's why we use machine learning today. And when you look at so there's a question if the registration for the Cronus challenge is binding. Yes, if you sign up for the Cronus challenge, you can't switch to a different project. And that's why if you want to leave in the meantime, you can leave the group then in this iLearn course, but the portal will close next week, Thursday. And if you don't want to do the Cronus challenge, but you have picked currently a spot, then leave the spot so someone else can still sign up. But whoever has signed up on next week, Thursday, at midnight, that's binding when the portal closes and you can't change anymore. And if in the meantime you don't want to do this any longer, or there's still, I think, one student who is, well, not anymore, he's not alone anymore in the group. If you don't want to do the Cronus challenge, then leave your group so someone else can still sign up, because I really want to fill the 40 groups for next week. So we'll have maximum turnout. But since there were a few times also here questions about the marking, either a regular project or the Cronus challenge can lead to a really good mark. And this ranking of the top three mainly is about the prize money, not too much about the marking. So, but the prize money is interesting, and I think it's a great incentive in addition to having lots of fun competing in that Kaggle challenge. The kickoff in 2 weeks with Cronus will not be recorded because it's only on campus, and that's why you also need to be present. to actually then sign up in the Kaggle portal and before already create your Kaggle account so it's all up and running when we do the kickoff in 2 weeks. And Kronos, they too had other approaches in the past in their inspection machines, like various filters or templates or whatever, or statistical shape models. They had different approaches and different filters. But the challenge they faced was customizing this to concrete other customers, so that had other bottles. And with deep learning, they saw that they can actually classify much better and they have less work for customization to adopt this to a different customer. But rather, they need a few more training examples, but they don't need to manually change the filters too much. So that's what was the incentive for them. And when I was in charge of the AI competence center at Kronos, we helped that group with some technical support building this, and then later it became available as a product. When I was there, it was in the R&D phase, and now you have the chance to beat the system from that time that is currently available in production. So I think it's a cool opportunity. And there has been a lot of progress in methodology because there are now better convolutional neural networks. There are transformer models. So a lot has changed since that R&D phase. And I guess since 7 years ago, they still have spent more time on R&D. How much exactly? I don't know. I left Kronos like 7 years ago, and then shortly after that got my professorship here. But well, I think will be a lot of fun, and we'll be happy to see you compete. Then last week we started with convolutional neural networks, and neural networks are so interesting because they allow that we not only learn a task like classification, regression, or some unsupervised task, but rather we learn also the features on our own. And as you know, feature description is a challenge, in particular in computer vision or, I don't know, in audio processing. And then with neural networks, we can self-learn features plus the actual task. And we saw how neural networks work. We saw their ups and downs in history. We saw how we do a forward propagation. And the forward propagation only works well if our weights or parameters are set to the right values. And that's why we need a cost function or error function or loss function, whatever you call it. And with that, we can then determine how good or how bad our model is. And we want to reduce that error. But to reduce the error, we need to update the weights. And we saw different error functions. And then we saw for one example how we could find the minimum for that one weight. For one weight, we could also just use an analytical approach, but in a real neural network, we have millions or even billions of parameters because each connection in there is another parameter. And we saw different approaches, how we can do this with gradient descent, which works, but it's quite slow. So there's stochastic gradient descent and many more optimization algorithms nowadays. The question is, how can we get these actual partial derivatives? And there's back propagation, but that still depends a lot on the actual architecture of the model. So that's a question we've discussed later in that chapter. And with deep learning, we have a lot of hidden layers, and then we can self-learn better features or hierarchies of features. That's what we saw last week. With this deep learning ecosystem, we also use different activations functions now, not just sigmoid, but RailU and a lot of variations of RailU. And then we saw convolutional neural networks, which apply this concept of convolutions to our 2D data that we can then feed into a neural network. Because with a classic neural network, we can only feed in vectors. And turning a 2D image into a vector, we lose a lot of spatial information. And with a convolutional neural network, we retain that. And what we often have is a combination of convolutional and subsampling layers. Sometimes the subsampling layers are called pooling layers. And then we saw a couple of elements that convolutional neural networks have, like spatial interaction, spatial arrangement, parameter sharing, as well as equivariant representations. We've discussed this in detail last week. And then we saw what such a convolutional neural network would look in practice. We have the 2D input, then we have different convolution and subsampling layers. And just for the very end, we have like 2 or 3 hidden layers for the actual learning the task that we would have here, like classification, regressions, or most of it is the feature detector. We can also visualize units, and we saw we need these partial derivatives, but we somehow need to determine where these partial derivatives come from. Backpropagation is one thing, and we can do backpropagation, but for that, we need to derive analytically a solution for these partial derivatives. But if we want to try different architectures, make a lot of changes, that's a lot of work and it's quite slow. Other approaches are also slow, as we saw last week, where they have other downsides. And that's why the approach today that is most common is automatic differentiation. So we can easily manipulate the architecture, other settings, other hyperparameters. We can change the cost function, and we don't need to worry about how to determine the partial derivatives manually anymore. We saw Keras as one example, and model selection is something we've discussed, and AutoML as another abstraction approach. And we saw we can speed up using GPUs, for example. And this is where we were last week. And now there were some questions also here from the students in the chat with regards to the Cronus challenge. Do you need to come up with your own model? Can you use a existing model? That's exactly what I want to share today. So when you train a neural network from scratch, that's quite challenging because you need a lot of training data. So a bigger neural network with more parameters means you need more data. And if you don't have enough data, a lot of statistical models or machine learning models, they tend to overfit. And overfitting means you work very, very well on your training data, but you don't work well on data beyond that. And so you've learned the details in your training data too well, actually, and you don't generalize. That's what overfitting means. And to prevent overfitting, there are lots of different approaches, and one of them is maybe reducing the parameters, but still you need a lot of data. Plus, what's the architecture of your neural network? How many hidden layers, how many convolutions, which settings in the convolutions? And that's a lot of trial and error. And I've mentioned before these hyperparameter optimization techniques, which were here, like grid search, randomized grid search. There was always this joke saying graduate student optimizations, or a graduate student in the US world is a student doing a PhD, doing a research degree. And graduate student optimization would mean someone spends his or her entire PhD just on finding new architectures, trial and error, hoping some of that works. So I don't know if you heard this term before, graduate student optimization. So it means building your own model may take very long, not a lot of fun. And that's why what we want to use are best practice architectures that others have found, have spent a lot of time, a lot of trial and error on it. And maybe we can reuse them so they are pre-trained on large data sets. And we can either use them or we can still fine-tune them with some additional data. So maybe now for the Cronus challenge, where imagine you can take a pre-trained model that works very well on a lot of different vision tasks because it has very good feature detectors plus a good classifier. Now we want to work on bubbles, and it's just a binary problem then, determining whether reusable or not reusable. So what we need to change is the classification layer. Maybe we just need finally 2 outputs or just one output eventually, whether to reuse or not reuse, but we could keep these well-trained feature detectors. Maybe we don't need to touch them at all anymore. All we need is on our extra data from Cronus, we need to fine-tune now, not touch the feature detectors at all, maybe just train actually now the classification layers at the very end. And then 50,000 examples are more than enough to do this. If I trained from scratch, I would need way more than 50,000 examples. Obviously, you could try to still fine-tune your feature detectors. You could do that if you wish, but maybe they already work extremely well because they were trained on a huge data set with lots of variation, and all we need is to update now the classification layers. So what does that look in practice? I want to present a few selected architectures that have become popular, and probably the one that became super popular and created this whole deep learning computer vision revolution that we've been witnessing for the last here 14 years then, is the AlexNet. The AlexNet was trained on the so-called ImageNet dataset, and ImageNet is a dataset. There are different versions of it. The 2010 version has 1.2 million images and 1,000 classes. So that means if you want to build a neural network that can classify into 1,000 classes, you need 1,000 output units. And you need input units, and the AlexNet had something like 650,000 neurons and 60 million connections in there. Maybe not everything fully connected, we'll see it in a moment, because fully connected is not always the right thing, but some architecture was found. And this was trained on the ImageNet dataset, and it achieved a so-called top 5 test error of 15.3%. So what's a top 5 test error? That means if you have an image and you classify it, you are predicting eventually a value per output unit. And what you would take is you would take the output unit with the largest value and say that's the class. But then if here this means you take your top 5 units, so the units, the 5 units with the strongest output, and if one of them is the right class, because these images have their right class in it, then you would be fine. So if you make your top 5 predictions and one of them is the correct one, that would be fine. And the test error, so on the test set, the top 5 test set error was 15.3%. Do you think 15.3% is good or bad? If you think it's okay, maybe thumbs up. If you think it's bad, maybe thumbs down. For that time, it was really good because for other approaches that did not use deep learning, they maybe had an error of like 30 or 40% or something like this here. So top 5 test error. What was often done was they used, so in the time before that, or what was often used were support vector machines that used features that came from some feature detector like SIFT or the other feature detectors we have seen. But that led to quite big errors. And the 15.3% on this ImageNet dataset the ImageNet dataset was specifically made so people can challenge each other, build new models. And this was a big improvement, these 15.3% top 5 test error. The AlexNet is named after the inventor Oleg Krzyzewski, and he proposed that and published it in 2012. And what you can see here was you have the image input, you have convolutional layers, you have pooling layers, and you have a combination of those, and then you have your 1,000 output units. And just before that, we have 2 hidden layers with each hidden layer has 2 times 2048 units, and we have 2 hidden layers. So that's the actual classification part. The other stuff is the feature detector part. And this was a big improvement at that time and sparked a lot of interest in convolutional neural networks. So convolutional neural networks had been proposed originally in the 70s and 80s, but then this interest in neural networks dropped for historical reasons. And here for computer vision, it really revived. And that led to a big revolution. So a model that was then became popular is ResNet. It was proposed 10 years ago. It employs a so-called residual neural network. A residual neural network does not just connect units from one layer with the next layer, but sometimes skips at least one layer, so connects to later layers. That's a residual connection. And this is something that was proposed, and there were different proposals of the ResNet with different layers. So one of them had 152 layers, and the network ensemble, so an ensemble means a combination of multiple networks, achieved a top 5 test error of 3.5%. So you see this error of 15.3% gets slashed into a third, into almost a fifth, so fourth or fifth within 4 years. I think that's an impressive progress just in 4 years from the top 5 test error of 15.3% down to 3.57%. If you also think this is huge progress just in 4 years, maybe thumbs up if you think it is, thumbs down if you're not. So I think this was a massive improvement at that time. And it's something I also followed actively. So this was during my PhD time then, and I didn't work on computer vision in my PhD, but on data from power grids and smart grids. But I still followed this because it really spread all over the news. And there are different ResNets that were proposed at that time, and we see the residual connection, something like here, so that, for example, some convolutional layer is connected to the next one, but also to one 2 layers later, and then it's all merged together here. And this kind of stuff really would have not been possible without automatic differentiation, because this was a lot of trial and error. And if we needed to manually derive and implement the computation of the partial derivatives, be no way we would have had this innovation. So none of this would have really happened without the automatic differentiation, which became available just a few years before in a lot of deep learning libraries. I worked a lot on computer vision during my master's, just a few years before. And in my master's thesis, I focused on detecting facial emotions such as smile or not smile in faces. And I also built neural networks for this during my master's. So I did my master's in 2014, 2015, and classifying whether a face smiles or doesn't smile. If you look at previous works just from a few years before that used, for example, support vector machines on pre-computed features, they still had an error of some, or say an accuracy of 70, 80%, so an error of 20 to 30%. And I built a convolutional neural network in my master's thesis that then had an accuracy of 99 dot something percent. So the error was less than 1%, whether a face smiles or doesn't smile. And I also took advantage of that progress at that time. But then in my PhD, I didn't work much on vision, but on smart grids and data from power grids. But I was also there in that time and published my work. And it was just impressive if you had a smile recognition that was before an accuracy of 80%, then up to 99%. I think that was a very exciting time also for me at that moment. There are other best practices neural networks that have become popular. One is called YOLO. YOLO means you only look once. And YOLO, there are lots of YOLO versions. So YOLO 4 was the up-to-date one when I taught this course for the first time 6 years ago. And since then, a lot of new YOLO versions have been proposed. YOLO does a little bit more than the ResNet or AlexNet. So ResNet and AlexNet, they only classify the image. So they take the whole image and turn it into a class. While if we are more interested in other object recognition tasks, like something like this here, like we have multiple objects, we want to detect and classify them. This is what YOLO can do. The AlexNet and ResNet in the original versions could not. So we can locate objects and then classify them. And YOLO is really popular for this. And over the years, lots of new YOLO versions have been proposed. Like last year, YOLO V12. Um, the, but the research is diverging. There's also a YOLO version 100 or a 1000. So it doesn't mean necessarily that the official one is YOLO 13 or 14 now. It's just a lot of different research groups working on this. So the research has sort of diverged. But YOLO is very popular. Lots of students use something like YOLO or some other pre-trained model every year for their project. And you can use any pre-trained model for any of your projects, not just Cronus Challenge, also the other stuff. And the regular projects, and you can fine-tune them. Obviously, your project should not just be using a pre-trained model and putting your own images in it. You should still fine-tune it, make some changes to the methodology, integrate it into some workflow. Because remember, you're spending half of the term on the project. So I would not be very happy if you just download a pre-trained model and plug in some images and say you're done. So you would need to do more work, like fine-tuning, changes to the architecture and some pre-processing, whatever. Yeah, this is about YOLO. Lots of variations of YOLOs, YOLO for embedded systems or on the edge, whatever. There's lots of training material online, be it from NVIDIA. NVIDIA has a deep learning institute where you can watch courses for free. You can pay for some courses. As a student, you may get more free courses. So this is not marketing for NVIDIA. They are one of many learning content providers, but obviously NVIDIA has a big incentive in training more people in deep learning, so they buy more GPUs. And I told you, did I tell you last week that I met Jensen Huang last year? Maybe just remind me, thumbs up or thumbs down if I said this. So I said it. So very impressive person, and it was a lot of fun to sit together with him for an hour last year. There's one more thing I want to share now. If you're curious to study neural networks in greater detail, there is the TensorFlow Playground. Has any of you ever seen this? Maybe thumbs up or down if you have seen the TensorFlow Playground. So you find this at playground.tensorflow.org. And what you can do in here is, this is not for vision data. It's just for a regular neural network or regular deep architecture. So you have different data sets. So this here is probably the simplest data set. And the input is we have an x1 and an x2 coordinate. So it's 2D input. Plus we have these two classes, blue and orange. And up here, you can just click and train the neural network. And what we see is we learned the decision boundary and the training loss and the test loss is down to near zero. So training loss is the loss on your training data, and the test loss is the loss or error on your test data, which was not part of the training data. It's two different sets. And you can use this also for this data set up here. And we also learning takes a little bit longer. This we see, well, the learning works okay. Maybe the test loss can be further improved. And what you can change here is your learning rate. You can change your activation function. So there's not just sigmoid and ReLU, there are others, but maybe let's switch to ReLU. You can also set a regularization factor, which I will mention in a moment. And Now I can run this. We see this only runs slow because the learning rate is probably too slow, so we can speed this up. But if the learning rate becomes bigger, then it may overshoot, as we have seen last week. And if this doesn't work well yet, we can add maybe more hidden layers, more neurons per hidden layer, and we can train it. And now we see the error is quite down. All of this can be further complicated. We can add noise. So noise means these classes start to overlap, which will severely complicate our training. And we see the test error is still quite high. So I would need to build a more complex neural network. Um, Here I could feed in some pre-computed features, not just the X1, X2, but other features derived from X1 and X2. But we still see, this is quite overlapping these classes. So I could pick, for example, regularization with a certain factor to address the overfitting. Still not too great. And learning this year is actually not that easy because these classes overlap, as we can see. But you could try to work on this and see whether you can classify better. And this still here is a relatively simple data set. Obviously, we can reduce the noise, then will become easier. We see then it works well. And the real challenge is this spiral of two classes if you want to train that. And it's something maybe you and your classmates, you can challenge each other who can learn this the best. So with the network I've built here already, this looks quite okay, but we can still improve. And if you feel you have found a good architecture, you can just add more noise and will become again way more difficult. And we see this oscillation here is typically shows us there's some issue in the training, and we could try to address this in different ways. And you can play with these parameters. Increasing the learning rate too much typically doesn't help very well, and so it's something you can try at home, and you can try to find a solution to this problem. And if you need some more explanation, so you can also see the feature detectors here. They have been learned and visualized. And down here are some more explanations. Some of you have said they know the TensorFlow playground. Do you find it helpful for those who have tested it? Maybe send some signal whether it's something you found helpful or not in the past when you studied it. So some found it helpful. I find it very helpful personally because you don't need to install anything in your computer. You can just run it in the browser. And feel free to build your own neural network here in the browser to work, have a good classification of the spiral here. And if you think it's too easy, just add more noise and you see it will become even more difficult. So this is a TensorFlow playground. And we have finished the neural networks now. We will come back to neural networks again in the selected topics, which we discuss possibly next week, I think, already. We will see vision transformers, which is another approach using neural networks for vision, which is sort of the contrast to what convolutions do, but or a different approach than convolutions, but that's something we'll see next week. And today we will look at image sequence processing. So far, we've just looked at static images, and now we actually want to process a series of images. And in images, the image sequences, what they can represent is motion, for example. And then what we want to do is we want to track in an image sequence. So we want to track, for example, an object in a video. And for tracking, there are lots of different approaches. One approach is, for example, a Kalman filter. The Kalman filter is a very generic filter model. We will study the Kalman filter in great detail today and next week. But in order to understand it, we first need to study temporal models. And there will be a few other things like the correspondence problem, which describes an overall problem that we face in computer vision, in image sequence processing. And then we'll see a method also that is called the optical flow to assess movements in image sequences. And you can also use neural networks for image sequence processing. But since this is the computer vision course, and it's not called deep learning for computer vision course. We look here at various other techniques, and you can use neural networks for image sequences too, but again, they have pros and cons. They may require lots of training data, lots of hardware, while things like a Kalman filter or the optical flow, they need way less hardware. And the good thing is the temporal, like the Kalman filter, is a highly generic approach that can not only be used for vision, can be used for lots of other signal processing problems. And if you're curious about how neural networks can process image sequences, maybe this is something you would see in a deep learning course or advanced deep learning course or advanced computer vision course, whatever. But neural networks are not the only thing in computer vision, and that's why we look at some other methods. And even though they are more traditional, they are still extremely powerful. Um, and that's why we'll study them here in this course. Now, in computer vision, one subfield that is of interest in studies is motion. And when we deal with motion in computer vision, we want to see how things move in a scene. So motion adds a further dimension to computer vision because we have time. We not just have one image, but multiple images, a sequence, and maybe objects move through there. So in motion, we could think about tracking features, which we could then use to track objects. With our more classic methods, we need to first compute features and then track the features. In maybe with a neural network, this could be combined because we can learn both tasks together. We could also segment objects based on their motion cues. We could think about motion stabilization. For example, you have a camera and you keep shaking, yet you want a stable video recording. That could be an application of process or thinking about motion in computer vision, maybe surface structure, 3D reconstruction of objects based from a video or image sequence, dynamics in scenes, scene recognition, maybe collision detection in an autonomous car and avoidance of collisions. So there are lots of examples of motion in computer vision. And one of the use cases I have just mentioned is tracking in image sequences. And tracking means we have an initial set of objects in our first few images, and then we have more images in that sequence, but the objects may keep moving through the scene. So we want to create initially a unique ID for each of the initial objects, and then keep tracking these objects based on the ID and maintain the ID assignment. Where we can imagine this the best is, for example, in such surveillance cameras, CCTVs, that we have objects like cars that keep moving. And once we assign an ID to this minibus here or this van, we just want to keep that ID, for example, the color, and not just keep changing, but rather keep moving or see how it keeps moving. For this car, we've also tracked how it moved for the green car here. We see how it has moved, and this could be used for all sorts of applications around police, traffic inspection, and so forth. Yeah, welcome back from the break. Few more things on the organization. I have also meanwhile added Alexander's email address, so our contact person at Cronus. It's in the main page of the iLearn course, but I think so far there's no need to get in touch with Alexander course, all the details about Kaggle and all the technical stuff they will share in 2 weeks at the kickoff on site. For now, it's your task to join a group. And please also for the groups, update your group description. So there's always a match between your name and the student ID. Some groups have done this, some have not. For some, it's incomplete. So it would be good if you do this as quickly as possible so we don't forget this. These project presentations, they only take place on campus. So the Cronus Challenge, it's all on that one day in June. And that day concretely being June 27, it's a Saturday. That's the only day they're free, the Cronus colleagues, all day long. It will be a long day, and you're anyway supposed to attend all or you have to attend all the project presentations on the day on which you're presenting. So if you do a Cronus challenge, you need to be there all day. Don't be late, don't leave early. That's not possible. And if you do, uh, and if you do a different project, that project would be on the presentation either June 20, 21st, or 28. I will assign you to one day. You can't change that, or you can't pick the date. I will assign you to one of the three dates as the schedule allows, and you need to then attend all the presentations on the day of your presentation. You're welcome to attend the other days, but you have to attend the day on which you are presenting. There's a student who said they were two in the group and someone joined and you wouldn't want that person to join. Um, well, or for every student, you're not supposed to arbitrarily join a group that still has a third spot. Only join if that group is happy with you joining or that you know each other. And if you were two and you didn't want that third person, clearly ask him to leave, or him or her. Um, it's not like you have a right to join a group of two. You could have found a group on your own earlier before, because a lot of you had made plans and preparations before today. So if you join arbitrarily a third group and they ask you to leave, then leave and do join a different group that wants you to join or do a different project. But I'm happy that these 40 groups have already been assigned. Some still have a third spot, some don't, and that's also okay. But 40 groups will have a lot of fun doing these competitions. When we planned this challenge, I had also thought about doing multiple days or more than 40 groups, but their Cronus colleagues are only available on one day and they want to join all the presentations, and we also need to sit together and do the ranking, and that's why there's only one day on which we can also award the prizes. And yeah, the project presentations only take place on campus. Someone just sent me an email that he or she is abroad and whatever. You need to be on campus for the presentations. No online presentations are possible. And I'll tell you why. So after COVID, in the term after COVID, in my big data course that I taught at that time, I allowed students to present online as well if they had any unexpected problem, and said, I wish everyone was on campus, but exceptionally, you could present online if there was any major issue. And then, I don't know, like 30 or 40 students wrote me that their grandma passed away unexpectedly and they needed to present online. And then I said, well, in the following year, I said, well, in the previous year, my big data course killed like 30 or 40 grandmas, and this year I want your grandma to survive the big data course. And I think if there are no online presentations possible, less grandmas will die. So I know it's sort of a joke, but that's why we only do on-site presentations. Yeah, now we'll continue with temporal models. So our goal is actually studying the Kalman filter, a very powerful signal processing tool. And before we make it to the Kalman filter, we first need to discuss some foundations of temporal models, because there are a lot of temporal models, and the Kalman filter is a very specific one. And when I integrated a Kalman filter in my course a few years ago, I was wondering how to present the Kalman filter as easy as possible. It's a very tough tool, in fact, and if you look at books like Russell Norvig and others, it's a few pages that they assign to the Kalman filter. The problem is, in order to understand the Kalman filter, you need to know lots of other stuff beforehand about temporal models. And that's why when I wanted to add the Kalman filter to this course, it turned out to be not just a few slides, but a lot of preliminary foundations that we need to know. There's a question again about presentations on campus. All projects have to be presented on campus, not just the Cronus Challenge, also all the other regular projects in June. So we only do on-site presentations on campus, not online. I hope this has now ultimately answered the last question. Everything will be presented on campus at the end of the term and no exceptions. And now we need to think a bit about the temporal models. Temporal models, they allow us to process signals that have a time component. And we'll first see a few generic examples, and then we'll just start describing temporal models. And from there, we'll make it to the Kalman filter. But this will take a little bit, and we'll need some mathematical foundations for the Kalman filter. Now imagine that you're in a forest or in a jungle, whatever, and you see a bird, and this bird is flying, and you can see the bird, but sometimes you may not be able to see the bird flying because the bird is behind a tree or some bush or something else occludes the bird. So you still sort of make a guess where the bird could be right now, and at some point you will see the bird again and you make an update to your belief. This could also be applied to radars. For example, in World War II, we see this radar operator here, and you have every 10 seconds a wandering blip on your screen. And then you need to wait 10 seconds again, but still in the meantime, you would sort of make an estimation where that object or plane or whatever could be at the moment. And so you could do this with other objects, for example, planetary motion. You say in the early days when researchers tried to observe planets, they didn't see them all the time, but sometimes through their telescopes or whatever, and the planet may have not been visible, occluded, whatever. And still, they sort of estimated where the planet could be at the moment, and they had a lot of very noisy observations as well. And despite the noisy observations over time, they were able to describe the planetary motion, which was then turned into concrete equations. And this is what Kepler did a long time ago. Now you wonder, what does all of this have to do with vision? The first two tasks, we see a vision component. The third one also to some degree. And in fact, all of these three examples, they have one common task, and that task is called filtering or state estimation. So state estimation and filtering is two synonyms. So we want to estimate a state or state variables from what we've seen here, for example, position and velocity. And we make observations over time, but these observations are noisy. And we still want to estimate our current state. And why is this called filtering? Filtering means we want to filter out the noise and from the signal. That's the idea. So filtering and state estimation are synonyms. And our goal is to make it to the Kalman filter. Let's see if we can start with the Kalman filter today. Maybe, maybe not. Definitely next time then. And we want to make it there. And first, we need our foundations on temporal models. And this is from, I mentioned it before, the Russell Norvig AI book. And the chapter in there is called Probabilistic Reasoning Over Time. Who of you sometimes reads the Russell Norvig book or has spent some time on reading Russell Norvig AI, a modern approach? If you have, maybe thumbs up or thumbs down if you have not. Um, so some people read it, some don't. It's personally my preferred AI book, and I think it's certainly one of the most popular AI textbooks, or probably the most popular one worldwide, which covers lots of different stuff, not just machine learning, but other approaches as well, like logic, problem solving, and here also probabilistic reasoning over time. Um, Peter Norvig, I think he's largely retiring now. He was the head of research at Google. So big guy, also a lot into teaching and created lots of interesting online courses over the years. And he and Russell Norvig, he and Russell, Stuart Russell, they wrote this book, AI, A Modern Approach. And I think the current edition is the fourth edition, which appeared a few years ago. And Stuart Russell is a professor at Berkeley. I met Stuart Russell, a couple of times at conferences. He's now more concerned about AI turning out of control, AI ending the world, this kind of stuff, which sometimes is sort of surprising, but still the book is really cool. And even though I disagree a lot with Stuart about some of the stuff, I enjoy the discussions with him. Plus, when I met him the first time, I told him I'm a big fan of that book. And yeah, what we want to do now is we want to describe how a state evolves over time. So a state can be a position in an image sequence. It can also have velocity. States could be something totally different, like whether it rains outside or not, and we are unable to observe that state directly, but rather there is other stuff we can observe. And from this, we want to make, so we have sensors, we can measure stuff, and from this, we want to estimate various variables in our state. Now you wonder, what does this have to do with computer vision? Well, it's a very generic approach we can apply to lots of different signals. We can apply it to vision, for example, to features from a feature detector that is applied to an image sequence. And we then use these features and put them in our temporal model. And there are lots of different temporal models. You can use temporal models also for natural language processing tasks, for example. And a concrete one we will see in the course of that lecture as well as next week is the Kalman filter. And but it's generic. You can apply it to other data as well. And since I didn't see any other course in these AI programs that discusses these signal processing tools, I felt the computer vision course could be a great place to put it in because we can apply temporal models, particular Kalman filters, to vision, but also to other tasks. So I think that overall makes this quite interesting. So what we have now are time slices. So what we use for now on is a big X in bold at time t. And then we have different time slices. So we start with time 0, for example, or time 1. We'll see this in a moment. And then we have a next snapshot at time 2 and so forth. So it's discrete time steps. We are not thinking about continuous time. If we wanted continuous time, we could model continuous time, but we would need a totally different approach. Concretely, we would need stochastical differential equations, SDEs. With these, we could model continuous time, but again, in computer science, we're largely interested in discrete data, and here discrete time, so time steps or time slices. And there's not just x, so x is in bold because it's not necessarily just a variable, it's a vector, because a position could be xy coordinates, could be as well as z coordinate, could be velocity on top along these three dimensions, so the vector would have six elements. Or we could put in totally different stuff. And we'll see a few examples in this course. So that's our state. And we also have observables. So the state variables in this model approach is often not directly observable, but rather we have things that we can observe, so-called evidence, and the evidence is something we could see or notice and try from that to infer our state. And the evidence can be, again, multiple things we observe at a time, and we also have evidence at time t. And for a concrete set of values at time t, we use this lowercase e at time t. So maybe just confirm that you got the idea of this framework, that we have time slices, we have variable where we have a state which we can't observe directly, but there are things we can observe, and we have time slices. Maybe just thumbs up if you understood this assumption, or thumbs down if you didn't, because we will need all of this to continue now. So seems to be okay. So again, continuous time does not matter here in this course. For this, we would need a different modeling approach. Now we will look at some examples, and for this, so it's an example from the Russell-Norvig. It's not a vision example. I will mention vision examples later when we come to the Kalman filter. But with vision, we may have lots of different features which would severely complicate this example. We start with a simple example with very simple data, but it helps us to build an intuition for this model. Imagine you're now a security guard and you're stationed at an underground secret installation. And you always have to stay there and you want to know whether it's raining or not. But you can't go outside and observe this directly. That's forbidden. So you need to observe something different. And what you can observe is, for example, you have the director, and the director can leave and return, and you would then observe whether the director has an umbrella or not, and we try to infer from that whether it's raining today or not. So for every day t, we have this observation et, which in this case is even not a vector anymore. It's just a single observation. There is an umbrella or not. Imagine it could be more things we observe, but for now, we just keep it simple with this umbrella. So we have a variable now that we call umbrella t, or simply ut for short. And this is whether the umbrella appears or not. And our state variable is also just a single variable. It's not a vector anymore. It's just rain t or rt, whether it's raining. A simple state, a simple observation. And later we use some statistics to calculate whether it's raining or not based on our observations and previous observations. And we assume, just for the convention, that our state sequence starts at time 0. But for our model to finally work well, we assume we have a start state at t0 and observations come in as of the next time slice, t equals 1. So we start at t0 and evidence comes in one time click later. This will simplify how we build our statistical model. We can also have a notation A colon B. That's a sequence of time slices from A to B where both A and B are inclusive. So if we say XAB, this would denote the state variables or the set of variables from XA, so X at time A, up to time B. So this is an interval of time. So as an example here, if I have U1, 3, this would be the variables U1, U2, and U3. Now we need a couple of extra terms. And once we have defined them, we will start looking into an example in a few moments, and then this will become more concrete. But our state estimate contains uncertainty, and so do our measurements, because our measurements may not be correct either. Maybe we don't look precisely and we missed the umbrella, or we mistook an object as an umbrella while it was not an umbrella. And especially when it comes to vision or other signals, there can be a lot of noise and a lot of uncertainty, like in vision, for example, occlusions or illumination, whatever. So what we need is a so-called transition model, and the transition model would specify how the world evolves over time. So it rained yesterday. Does it rain today? That's the question. But we also need a model that allows us to plug in new evidence. And that's the sensor model, because we have sensors, we observe stuff, and we need to think about how these evidence variables get their values. And that's the sensor model. And for this first part, the transition model, so how our state evolves, we can describe this with a conditional probability. And here, in fact, this is not just a conditional probability, it's actually a conditional probability distribution, because it's a bold P. You all learned about conditional probabilities, maybe in school, maybe not, but definitely last semester in your statistics class. Who of you feels okay with conditional probabilities? Thumbs up if you don't feel okay with conditional probabilities. Also let us know. You would then need to do some revision, but we'll look at some examples and then see that it's actually not that difficult. And what this probability distribution, that's why it's in bold, P bold, it's a probability distribution. We say the distribution of xt given the previous values of the state from time 0 up to the previous time click. So xt depends on its previous values. Now, it's a distribution, because I not only want a conditional probability, but I want a conditional probability distribution. So the bold one here makes sense. Now we have one challenge. This one here is unbounded. As time evolves, it starts with t equals 1, t equals 2, and then say t equals 1000. That means the conditionals get longer and longer. They are unbounded as the time increases. And that's a problem, because this would complicate our computations a lot. It would slow them down. We would probably not have enough data to get proper estimates. So we need to do something to keep this bounded. And that's a Markov assumption. Who of you has heard about Markov assumptions before? You have just thumbs up. So some have, some have not. We'll see, this is actually not that difficult now. With a Markov assumption, we say that our state does not depend on the unbounded one, but rather we bound this, that this would only depend on the last few t's, but not all of them. So we have a finite fixed number of previous states that we depend on, and that's the Markov assumption. It goes back to Russian mathematician Andrei Markov, who introduced so-called Markov processes or Markov chains. They come in various flavors. So we need to simplify this conditional probability distribution where we said xt depends on all the previous x's from 0 up to t minus 1, which we don't want. We could say, well, our xt only depends on just the previous one. And that would be a so-called first order Markov process or first order Markov chain. So our state only depends on its previous value at the previous time click, and the other ones before, they don't matter anymore. We can obviously further complicate this. So we have a first order Markov process, which just saw that xt only depends on xt minus 1. We could say that xt depends on the last two x's, so xt minus 2 as well as xt minus 1. So we have this comma here, and we say xt depends on the last two previous time slices. We can visualize such a Markov process. What we see depicted here is a so-called Bayesian network structure. So Bayesian networks is also part of statistics and partially machine learning. And we can also visualize them. That's why Bayesian models or Bayesian networks, they're so-called graphical models, which is a broader class of statistical models. The good thing is we can easily visualize them. So we see our xt only depends on xt minus 1, xt minus 1 only depends on xt minus 2, whereas xt plus 1 depends only on xt and so forth. So this would be the first order Markov process. The second order Markov process that we had written down here can also be visualized. So xt depends on xt minus 1 as well as xt minus 2. So xt has two incoming edges, one from t minus 1 and t minus 2, while the t plus 1 has two incoming ones too from xt and xt minus 1. So the second order Markov process is maybe gives us a better estimate, yet calculating it is maybe more time consuming. We need more data and so forth. Maybe just confirm if you understood this difference here in this visualization of the first order and second order one, so how they differ. Looks okay. So, there's a question that I got in private here. The question is if these temporal models are conceptually similar to time series forecasting. Time series forecasting is a huge topic. You can use lots of different approaches. And yes, you could use temporal models for time series forecasting, but you can use lots of other approaches too. We will come to forecasting later. With forecasting, we address something different because we are currently in filtering, we will formalize filtering in a moment. So filtering means estimating our current state, while forecasting would mean looking into the future. And with our temporal models, we can also look into the future, but for this, we don't use filtering. And so far, we've talked about filtering. We will formalize it, and then we can look also into forecasting, which is also in the slides. So I hope this addressed the question that you had well. But we'll formalize filtering and forecasting and all of this. We're still in the early phase defining all of our components. The next definition we need is a stationary process. A stationary process describes the following. Obviously, we have dynamics in our temporal models. So state variables get updated. But what is a stationary process? A stationary process means, and we will always use stationary processes, that these laws that govern the updates, they don't change. So the rules of how we update in the model, with which conditions and so forth, this stays the same. Obviously, the values get changed over time because it's a temporal model, but the rules of how we update does not change. So that's a stationary process. If you said there was a static process, a static process sounds very close to a stationary process. Yes, a static process, from my definition, would mean that a static process is not dynamic. So it's actually just the same values all the time. They don't get updated. But, and I've also written that here, in fact. So we don't deal with static processes yet, because yes, variables keep updating, but what we don't change is the rules of how we update. And that's described by a stationary process. So we've seen this transition model, just which was here, and we applied the Markov assumption to it. What we need is next a so-called sensor model. And the sensor model deals with the following things. So we have evidence variables, so the kind of things we can observe, but again, observations are uncertain too. There is noise in observations. And so what we observe at time t could also depend on previous variables. For example, on previous observations, but also on our current variables. What is actually in our state variable that could impact of what we can actually observe. So we need to model this. So, because our observations, they are also uncertain, they contain noise. So the probability distribution of our evidence, so what we are observing, depends on our previous states up to the current state, in fact. So x0 to t, plus it depends on all the previous evidence. So the observation that, or the probability of our evidence at time t depends on all the previous states, as well as all the plus the current state, plus all the previous things we have observed. Do you think this is something practicable that we can work with? Do you think this is reason? I mean, it's probably a very, very good assumption, but do you think that this is something we can use in practice and work with? Making such a tough assumption. If you think this is fine, it works, thumbs up. If you don't think, maybe thumbs down. And some more interactions would be great, please. There's a majority of students who think it's not very reasonable. Well, it's obviously correct to assume this, but a model is always a simplification of reality. And we need to make sure our models can actually be used, that we have enough data, that we can do the updates quickly. So what we would say is we can simplify this. Here we make a sensor Markov assumption and say that the probability of our evidence only depends on our current state, on the current state, not the previous states, not the previous evidence. So it severely simplifies this model. And this model is the sensor model. So the probability distribution of the evidence at time t given our state at time t. And what we have here is the sensor model, and the sensor model is sometimes also called the observation model. Now we will come to an interesting example. And this example is something I will develop with you on the whiteboard. So just allow me a quick moment for my iPad to sign in and screen share. So this will just take a short moment. So, now look at a real world example for to understand what the transition and sensor models actually are. Back to our rain and umbrella. So we want to see an example of the transition and sensor models. So the key to us is we want to know if it rains today. So nice R at time t. And this will depend on if it rained previously, so yesterday. That one will also depend on something. And we want to know then also how does having rain tomorrow depend? So rain at time t plus 1. It's all well formatted in the slides, and we'll see the image later again. So we need to describe the first part of is the transition model. So how we can model transitions without the evidence. Evidence will come later. So we need a table for this. We need to know the probability. So we do the distribution, but we write out because it's only true or false whether there's rain or not. So we want to know how does RT depend on RT minus 1, so whether it rained yesterday. And we want to know depending on if it rained yesterday or not. So yesterday it may have rained, true or false. And if RT minus 1 is true, so if it rained yesterday, I can try to write the T a little bit nicer, then the probability of having rain today, if there was rain yesterday, is 0.7. And if there was no rain yesterday, the probability of having rain today would be 0.3. So this data just comes from the example in Russell Norvig. Now I'm asking you, so it's the probability of having rain today given rain yesterday. My question to you is, just to revise your skills, do these two numbers, do they need to add up to 1? Thumbs up if you think that these two numbers need to add up to 1, or thumbs down if you think they don't need to add up to 1. So something yes, something. So some students say yes, and some say no. Maybe those who think yes, they can send to the chat why they think this needs to add up to 1. And the others who think it doesn't need to add up to 1, they also send this to the chat. And we'll compare in a moment. In the meantime, while I wait for your answers, I already write down the observation part. And I'm just preparing this a little bit now. And now wait for your answers. So, um, one student thinks they need to add up to one and says I should correct if he or she thinks that's wrong. And some people said they think these two numbers don't need to add up to one. So I would want to wait for their answer. Um, First of all, well, I'll wait and see if anyone else is sending a comment here as well. One student wonders if they are mutually exclusive, and that's why they would need to add up to one. Well, these two numbers, I'll reveal you now, they don't need to add up to one. This is a pure chance that they add up here to one, because what would need to add up to one is the following. So a quick excursus. If yes, it's a binary variable, but what needs to add up to one is the probability of RT given RT minus 1 with, so we sum this up with the probability of, say, having not rain yesterday, given, sorry, not having rain today. Well, it's not written very well, I'm sorry. I'll update this. Given RT minus 1. That sum would need to add up to 1. So it rains today, given it rained yesterday, or it does not rain today, given that information from yesterday. That needs to add up to 1, obviously. But what I see here in this table describes the probability of RT given RT minus 1. And RT minus 1 is from yesterday. It's this part here. And then, obviously, if it rained yesterday, then there's a 0.7% chance it rains, or if it rained yesterday, that's why the true, there's a 0.7 chance it's raining today. And the other one, and that it does not rain today, given it rained yesterday, that would be 0.3, but that is not denoted by that 0.3. That 0.3 stands for that yesterday it did not rain, and today it rains, given it did not rain. It's just pure chance that this adds up to 1, because this variable is for the condition, not for that one. Maybe just confirm that you got it, that this is pure chance they add up to 1, and they don't need to add up to 1, because a lot of people may just misinterpret that. So we could have totally other numbers here, and obviously the probability that it does not rain today, given it rained yesterday, is 0.3, but this is not denoted by this 0.3, but rather for a different value of the condition. So this was just to double check your skills from the previous lecture, which was, or from last semester in statistics. And so this is our transition model. And so we can think about our sensor model. In the sensor model, before we said something like, so here I'll write transition model. And in the transition model, we defined before that the probability distribution of xt only depends on xt minus 1. In bold, because it's a distribution, but I wrote out the distribution here in the table. That's why these are just single probabilities in the table, not distributions any longer. And it's just single variables, so we don't need a bold X here, but it's just observations whether, or it's sorry, it's not observation, it's just value whether it rains or not. So that's the transition model. And And then we have the sensor model. For this, in the sensor model, we said that the probability distribution of the evidence, so in bold times t, at time t, only depends on our current state. And these arrows here, they show this dependence. So they show RT depends on RT minus 1. This is shown by here. And then we have this dependence where the evidence depends on the state. This is shown here. So that's why these arrows, they show the condition, the dependence. When you took the statistics course and you learned about conditional probabilities, did you ever see that they were visualized with such a graphical model? Maybe thumbs up if you've seen such visualizations of dependencies, or thumbs down if you have not. But I think the visualizations, they help a lot to actually show how these variables depend on each other. So you haven't seen this. Do you find the visualization helpful? Is this something that makes it more understandable? And here I see some positive responses. So the sensor model can be we can also provide an example for this now. So in our table, what we care about is the probability of seeing an umbrella today, given it rains today. And depending on if it rains today, which can be true or false, we say if it rains today, then the probability of having an umbrella today is 0.9. And if it does not rain today, the probability of having an umbrella today is 0.2. So and these two numbers don't add up to 1, but they don't need to, because this variable is for the condition, not for the part here. So, and we can read this: if it rains today, the probability of having an umbrella today is 0.9, which would mean if it rains today, the probability of not having an umbrella today would be 0.1, because the 0.1 and the 0.9 need to add up to 1. And this one reads as if it does not rain today, the probability of having an umbrella today is 0.2, which would then mean if it does not rain today, the probability of not having an umbrella is 0.8. So maybe just confirm if you understood now how to read these tables and to know what needs to add up to 1 and what does not need to add up to 1. So, seems to be okay now. And with that, we can switch back to the slides. So all I had shown you before is this figure here from Russell Norvig, yet I think it makes sense to develop it step by step and see what actually adds up and what doesn't add up, rather than just showing you this whole figure up front. We just wrote in short R instead of rain, or U instead of umbrella, but still the same content eventually. I've also told you what the arrows mean because they show dependencies. And then in such Bayesian models, I told you we would have observations, so evidence, as of the time one evidence would come in. But I need to start with some initial state, and x0 is the initial state with which I need to start, and I need a probability distribution of the time I'm starting. Then these Bayesian models, they can be described, or their structure, because we have defined the structure now and we have made up these probability distributions. Yet you could have a totally different structure. You could say whether we have an umbrella depends on, say, if it rained yesterday or not, or some totally other relations we could express in here, and how we have these conditions or this structure, we can describe this as through a complete joint distribution. And the complete joint distribution here of all the states and all the evidence would be we start with an initial state, and we know this is the transition model that our state depends on the previous state. Here we have variables I, and I starts at 1 and goes to t, plus we multiply in this product that the evidence, the current evidence, depends on the current state. And to go from from the first time click, which was 0, evidence and transitions come in as of time 1 up to t, we have a big product where we multiply all of these together for I from 1 to t. So with such a complete joint probability distribution, we can describe the structure and the dependencies. Eventually, this just shows what we had shown here. The only thing that we didn't have in here would be that we would also need to consider the rain at time equals 0. So we would have this here and would multiply it in there, because whether there is rain then at time click 1 only depends for now on rain at time click 0. So this graphical model here, or this visualization, pretty much describes this. We've only added this for further clarification. And this was the transition model, plus we have a sensor model. Now, we've defined the structure of the model. Now we want to do different tasks with it. And one task is filtering. One student before asked about prediction in a private message. Prediction is a different task we could do with such a model. So we can do different inference tasks. So filtering is estimating our current state given noise. Predicting means looking into the future. So from the information we have at the moment, we try to look into the future. We can also think about smoothing, meaning we have evidence now and we can go back into the past and try to tidy up a little bit or get better estimates for the past based on new evidence we got. There's also most likely explanation. So we would have a path and we want to know what was actually the evidence to get there. Plus, I had these probabilities here. Somewhere these probabilities need to come from. For now, we've just assumed that they are made up. What we could also do is we can actually learn them from observation. So that would be a different task. So we have 4 different inference tasks in these models, and we can also do learning to learn the conditional probabilities. And now we will look into these 4 inference tasks. We'll spend most time on filtering because our goal is to get to the Kalman filter, which we will see next week then. We won't make this today anymore. And Kalman filtering, so for Kalman, in a Kalman filter, we have some extra conditions or we make some other assumptions. And in a temporal model, we just look at this from a very, very generic perspective of how we can describe filtering. And then we'll see how we can describe prediction, but we'll mainly focus on filtering. And the good thing is, this could be features from vision. It could be something totally different. It could be just whether there's an umbrella or not, but could be features from a feature detector. So the beauty is all of this is highly generic. And now let's look into filtering. So in filtering or state estimation, we want to estimate our current state that we can't observe directly, like we've seen before, whether it rains or not. And what we compute is the state estimate. Sometimes this is also called the belief state. So we believe a state that we have got. And the task is called filtering or state estimation. Filtering, I've said before, that term comes more from signal processing and early works in signal processing, where the problem was to filter out the noise in a signal because we want to estimate its underlying properties. So get rid of the noise. And what we want to compute is in filtering concretely, we want to know the distribution of our current state given all the past evidence. But computing this directly is not that easy, so we need to do a couple of other works around it. And with filtering, we would want to calculate this, but you see, it will be a bit more tricky because this can't be calculated directly. And in filtering, as we've said before, is we want to know whether it rains today, given all the previous observations that the umbrella carrier has made so far, because the evidence would be all the times we have seen whether the director brought in the umbrella or not. And we'll see how we can actually pose this as a computational problem. Concretely, we can't really calculate this directly. It's just not practical. It's the curse of dimensionality, or we just don't have enough data, and it wouldn't be very efficient to calculate this. So what we could say is, if I want to know, say, my state in the next time click, given of all the evidence from 1 up to that next time click, somehow maybe I could calculate this if I have my previous probability distribution at time t with all the evidence, and I have new evidence coming in at that one time click now on which I'm progressing. And somehow I want to combine these two, so my previous probability distribution and the new evidence, through some function f, lots of ways what the function could look like. So we combine this and factor this in, and we calculate the new probability distribution. And we see, so xt depends on xt, then, sorry, xt plus 1 depends on xt. Xt could depend on xt minus 1 and so forth. So this is actually a recursive problem description, which we call recursive estimation. And if we use recursive estimation, calculating this new probability distribution becomes much easier. So we take the previous state distribution and plug in new evidence. And there are lots of ways how we can describe this. And for that, we need Bayes' rule. I'll share the iPad again. Who of you feels fine with Bayes' rule? Thumbs up or thumbs down? If Bayes' rule is something you feel comfortable with, or if you don't. So everyone feels comfortable. Now let's see how much you know about Bayes' rule, but it's an important piece, but we'll do still a quick revision of Bayes' rule and an example. So Bayes' rule means I want to calculate x given z, and x and z can be whatever, but I'm unable to calculate it directly, so I can calculate p of z given x times p of x divided by a normalizer p of z. Is anyone in here who has never seen this? If you've never seen this, maybe just send a thumbs down or something, because I know there are exchange students or students from other programs, but I think everyone should have seen this. So, but we'll look at an example also for revision. There are a couple of names for these elements in here. What I want to calculate is p of x given z That's called a so-called posterior. For that, I need this one here, which is the P of Z given X. It's called the likelihood. We have P of X, so the probability only depends on X. That's called the prior. And because this may eventually lead to unnormalized probabilities, I need P of Z, which is something I call the normalizer. Sometimes this is called a marginal likelihood or something, but I very much prefer to call this a normalizer. It just leads to we have proper probabilities. But the normalizer can be left out and replaced with a different symbol, as we will later see, just to make the notation a bit more convenient. Now we'll have an example of Bayes' rule. So we're not in temporal models yet, or at the moment we're not in temporal models. It's just classic data, but just for us to feel comfortable. What we have is, and I'll tell you this orally because it's also in the slides, or I'll quickly switch to the slides so we also have this in the recording adequately. Um, so the Bayes rule, we have the following example. 0.8% of people have a disease D. Whatever the disease D could be, COVID or cancer, whatever. 0.8% of people have this disease. Now, you take a test, D, or you take a test for D, and that test ca is maybe sometimes not fully correct. So there's uncertainty in it. So it returns a correct positive 98% of the time, in the correct negative 97% of the time. And now you take this test and it returns positive. Now the question is, are you really sick or not? All you've taken is a test. Do you think you most likely have the disease or not with that setting? You maybe a thumbs up. Yes, the test returns positive, so I'm sick. Or that would be a thumbs up, or a thumbs down would be that you disagree here. So everyone thinks they don't have the disease most likely. So let's look into the numbers. I know you may have seen this in your statistics course, yet it's a good revision because we'll need the Bayes rule a lot from now on for temporal models to define way more complex temporal models. So we can say here for our example of the D test, we said that 0.8% of the people have the disease D. So P of the disease is the prior. This is 0, not 008. Very small because 0.8% of the people have this disease. Then we have the correct positive and the correct negative. So we had a correct positive, which was 98%, and the correct negative was 97%. So the correct positive would mean, given the disease, I get a positive test. So P of D, given I have the disease, is 98%, while the correct negative would be given I don't have the disease. So this is the negation. Given I don't have the disease, I get a negative test. Now you took your test, and what I need to know is, do I have the disease given I have a positive test? And all of you answered and you said you don't have the disease. Maybe for those who have not looked into the slides, because in the slides we have the solution, but I want to calculate this with you. What do you think is the probability that we have the disease given our positive test? just estimate what you would think the probability could be given this information here. Um, Please don't look in the slides. You can just guess a little bit what's the probability of having the disease given your positive test. Please send a few guesses to the chat. And there's nothing really wrong you can do here. I just want to see what you estimate. So one student thinks 30%. Someone thinks it's a very, very small probability, like 0.5%. Someone thinks someone thinks 40%. So we have 30, 40%. Someone thinks around the 0.8% or even less than that, like 0.5%. So we see quite some estimates. What I saw during COVID was a lot of people thought they have a positive test and they thought they are definitely sick and they will definitely die. However, I had such examples in my slides when I taught a course at a different university before I got a professorship long ago, and this is an example used long before COVID. But we'll come back to COVID in a moment, and see what happened there. So what we can calculate now is the probability of the disease given a positive test. Someone thinks again around 0.8%. So we can try to calculate this, but we're unable to get this directly from our variables. But what we see is we have the D given positive and we have a positive given D. And actually, we can just plug this into our base rule and we can try to compute it. So P of D given the positive test could be expressed as the probability of a positive test given D. Then I need a prior. This was this P of X. So this part here. So this would be the prior for a disease divided by the probability of having a positive test. So what we have in our table are the first two entries, this one here and this one. This one here, we don't know yet how to calculate it, but we'll see. So let's give a try. The probability of a positive test given the disease is 0.98 and the prior is 0.008. The problem is I need to calculate now. So I can just multiply those, obviously, but I would not get a proper probability. I still need the normalizer. And it turns out that this normalizer, P of positive, can be calculated the following way. We can say it's, for this we need another law, the law of total probability. We can say that this is the probability of a positive test and having the disease plus the probability of a positive test and not having the disease. Very importantly, we have these commas here. So this means an and, in this case, a joint probability, not a condition. So this comma here really has a purpose. It's not a condition. So that the probability of a positive test means it's the probability of a positive test and having the disease plus the probability of a positive test and not having the disease. Anyone has seen this law of total probability before? Maybe thumbs up or thumbs down. Now, the problem is still we are unable to get this from our data up here because we don't have this. We have some conditionals, but not these joint probabilities. It turns out we can calculate these joint probabilities in a different way. So we can say this is the probability of a positive test given the disease times the probability of the disease. So this would be in green. So I can calculate a joint probability as this product of a condition and a prior, plus we have then this one here. This would be the probability of a positive test given not having the disease times the probability of not the disease. And this is all largely available from our data. So here or in yellow, we have this one. And we can try to find these values now. In our data up here, P of positive given the disease is this value here, 0.98, and P of D was 0.008. So 0.98 times 0.08. So this is the green part. The yellow part becomes a bit more complex. What is the probability of not having the disease, P of not D, when I look at my original data? You can send this to the chat, what you think is P of not D. That's correct. It's 0 as 0.992 because having the disease and not having the disease needs to add up to 1. And the big question is now, what is this one here? The probability of a positive test given we don't have the disease. What is that value if I look at my data? And send it to the chat what you think is the probability of the positive test given I don't have the disease. Someone suggests 0.03, and that's correct because P of a positive test given I don't have the disease is 0.03 because this one and this one, they need to add up to 1 because my test is either positive or negative. And these two need to add up to 1 as we've seen before already. So this here then is 0.03. And when we calculate this, we get some number. You can use a calculator. And what we've calculated is the probability of a positive test. And that's the one we move in here in this fraction as the denominator, because our goal was to calculate P of D given a positive test. We have from the Bayes rule or Bayes theorem the likelihood and the prior. What was missing was this normalizer. Down here we've seen how to calculate it. We plug it in there, use a calculator, and we will get something approximately like 0.2.085. That would be 20.85%. So we took a test that was positive, and the question is, do we have the disease or not? Here we have a 20.85% chance. Some of you guessed a lot of different stuff, like 30, 40%, or a very small one. So the 30% guess was actually the closest. And there are a few reasons for that, because our tests are not perfect, because this one here is not one. But even if the test worked very well, or it works well with 98%, the disease is rare. And so we have a very small prior, which will reduce this product. Now, obviously, if you go to your doctor, the setting is more complex because when you go to a doctor, typically you have other symptoms, like you may feel sick, you may be bleeding, whatever, your throat may be hurting. Obviously, then a positive test has more weight because you have extra evidence. And with the base rule, you can update it, you can include more evidence like pain, bleeding, whatever. But if you just take a test out of the blue without any symptoms, this does not mean very much. And that's something that a lot of people sort of forgot during COVID. Obviously, COVID was a reality and people died and all of this, but just taking tests without any symptoms and without any further evidence, it probably, what you get out of it is not very, very conclusive, and the probability of actually having the disease is quite low. If you add more evidence, obviously, that probability will go up and it will go up a lot, as well as if maybe more people have the disease, if the disease spreads a lot, that probability will go up as well. Do you feel this example provided you some interesting insights into Bayes rule and testing? If so, maybe let us know if you found this helpful. This was largely now meant to provide you with an update or revision of the Bayes rule. So I see some of you find it helpful what we did because we need a Bayes rule in our temporal models. And so that's why this was just a revision. What's important is this part here now, and we'll combine the Bayes rule with the Markov assumptions. So in our temporal models, there is a task that we said we're first interested in is filtering. And what we just did before was filtering. We said we somehow need to combine the new evidence with the previous estimate of our state given all the previous evidence. And this can be done as a so-called two-part process when you look into this formula and rearrange it. So what we wanted was we said the probability distribution of our state that we can't observe at time t+1 given all the previous evidence up to the current evidence. And we can say, well, maybe let's separate the evidence. So here we set the evidence from 1 up to t+1, and we could just break up the condition and say it's the evidence from 1 to t and the new evidence. And then if you use Bayes rule, and I'm not showing you this in detail because this is now a highly generic temporal model. Later, it will simplify a lot when we make assumptions in a Kalman filter. But using the Bayes rule, because the Bayes rule can be used. If you have a question, let us know. Otherwise, any background noise will be recorded. And you can apply the Bayes rule to such a setting here as well. It's actually not that difficult to derive this. And then we can say, well, since we are unable to compute this directly in our two-part process, we can apply the Bayes rule and say, well, we can reframe this as the probability distribution of the current evidence given our current state estimate and all the previous evidence, and we multiply this with the probability distribution of our state given all the past evidence. So this can be easily derived with the Bayes rule. The only thing that is missing is the normalizer. And in a notation that we will use now, we don't really care about the normalizer. Normalizer can always be computed quite easy, but we don't want to write out the normalizer, so we deal with unnormalized probabilities. So we just put an alpha in front. Alpha here means unnormalized, still needs to be normalized, but the normalization is in fact, it looks boring on a calculation, but normalizing is actually not that difficult and we don't care about the detail. So we just put an alpha here. Then just for the wording, sometimes in Bayesian networks, there is a term called evidence, and evidence refers to unnormalized probabilities. However, in this lecture, we are building temporal models where evidence means what we observe through our sensors. So here, evidence really means the observations. If you look into Bayesian models and you hear evidence, it often refers to unnormalized probabilities. So this whole thing here could be called evidence, even though this one here is called also evidence, but refers to something totally different. Maybe just confirm if you got the difference between the two different things that evidence may mean. One's evidence what we observe in this setting, or evidence could mean unnormalized probabilities in general in Bayesian models. So it's two totally different things. Maybe just confirm whether you got that or not, that evidence here may mean two very, very different things. And because so this one here can be calculated okay. We'll see if this can still be simplified. But this one here is the tricky one because we want to calculate the probability distribution of the current evidence given the current state estimate plus all the old evidence. But that's why we introduced the Markov assumption, and we just kick out this part here, all the previous evidence. And then this here, in fact, is just our sensor model. And because we've said the probability of the evidence given the state estimate. And this last part here, this is a one-step prediction of the next state. And the first term is our sensor model. It's also written down here of what we had introduced before. Now, this one here, as I said, this can be simplified further. This can be calculated, in fact. And what I need to do is, because this one here, we already got our sensor model, but this one here doesn't really fit into our model so far. And we need to calculate this. And it turns out that this part can be calculated in a quite complex way. For this, if you want to see it in all details, look into the Russell Norvig book, but we'll skip it for here, or we skip it for now here, because later we will look into a concrete example, and then we don't need it in this generalization. And next week we start with the Kalman filter, and the Kalman filter will simplify this a lot by making some other assumptions. So if you're curious about this step here, look into the Russell Norvig book. And I know it's a lot of math, and it's still a lot of math when we look in the Kalman filter. The good thing is when we start looking into the Kalman filter, all of this will become simpler because this here is highly generalized. And later, when you work with a Kalman filter, you would probably anyway use some library to use it, but you still need to know how it works and what it's meant for. And that's why the math here is important, even though later you will probably not have to implement this on your own in your project. If you use a Kalman filter for some tracking or something, you would probably just use some library then. Now, we'll also skip this one here. Just some extra details. What we want to do is we want to calculate when we have a series of observations of an umbrella and not having an umbrella, we want to know in 2 days whether it rains, depending on if we saw an umbrella or not. And for this, we know this table here, and we've introduced it before. And so we know how to calculate if there's rain today, given there was rain yesterday. That's this table. And the sensor model is the probability of an umbrella today, given there's rain today. And we want to do this filtering process now for two steps to see whether it rains or not two time clicks away after having observed two umbrellas. But that's something we will do next time because I guess it was a lot of information for you today. We've had an intro to the Cronus challenge, and some of you may still need some further figuring out about the challenge, how you proceed, and if you allow a third person or not. And in the next lecture, we will do this temporal model. We'll see how we can calculate whether there's rain or not in the future based on observations. We will then look at also forecasting. There was a question today about forecasting. We'll see this next time. And then we will explore the Kalman filter, which makes further constraints, and it's something we can use then in order to have a model that we can use for tracking things or objects or features, for example, in an image or something. So we need a bit more theory next week. That's why until next week, revise the temporal models. Make sure you're familiar with all the terminology we've introduced today. The next week, we finish temporal models and continue with the Kalman filter, as well as some other methodology to work with image sequences. If there are no more questions, I wish you a good afternoon. There's still an hour left, and I'll see you next week. And take care and bye bye.